So just to introduce myself, my name is Mike McBride. I work in a Multicast development group, and I'm on the deployment team within that group. I spend the majority of my time working with providers in the interdomain space as they deploy multicast. So today, that's what will be discussed, is deploying multicast across the internet between domains. And here we go. The agenda that we'll go through is we'll first talk about the protocols that are used today to make multicast work. And that is multi-protocol BGP and MSDP. Those are the two primary protocols that is what is being used today and what is going to be used in the foreseeable future. I'll share a variety of examples of deployment scenarios of how this works, including how we're getting multicast to work here at Nanog out to the world. And then towards the latter part of the presentation, I'll be presenting the newer concepts of source-specific multicast, Multicast VPNs, and even more recently, multicast in the IPv6 world. So we have a lot to cover in an hour and a half. I'm going to be doing due diligence in getting through it all. I may have to click through a few slides rapidly to reach that goal, but I think we can do it. If there's any questions, feel free to yell them out. We won't be able to spend a whole lot of time getting into them, but we can discuss them as each section ends. Or feel free to send me an email. It's mcbride@cisco.com, or I'll be hanging around afterwards. Feel free to discuss anything you may have a question about. All right, so since this is not an intro to multicast presentation, I just wanted to give a brief overview of the piece that we will be discussing today. We're not going to get into exactly how PIM sparse mode works. I'm assuming that hopefully you already understand that concept, which isn't critical in understanding what I'll be presenting today, but it does help. So on the campus side, the enterprise side, there are protocols. Of course, there's hosts that desire to receive certain multicast streams. I know a popular one with the guys that I work with is the fashion TV streaming. You get to see all the models cruising around on the catwalk. So your host needs to find out which group this is. So they're going to send an IGMP report once they know which group it is that they want to join, and the IGMP report will be intercepted by a router, and that router will subsequently be able to forward that request out throughout the internet, throughout the network. Of course, there's typically switches, and switches have been optimized with a variety of protocols to make it so they won't just simply flood the multicast packets like they would with broadcast packets. So there are protocols out there that we won't be discussing today, but you can use to make it more optimized to have them sent out, the multicast packets sent out to certain ports. And then there's multicast routing protocols, the protocols that actually do the forwarding of the multicast traffic. There's sparse mode, there's source-specific mode, there's bidirectional PIM, and what we will be discussing today is multicast VPNs. And then we get into where we'll be spending the majority of our time today, and that is on the interdomain side, the protocols such as multi-protocol BGP, which makes it possible that we can control our multicast traffic between domains, and multicast source discovery protocol, which allows us to discover which sources exist so that we can join them, and source-specific multicast, which I'll go into some more detail as well. Throughout this presentation, I've been asked to try to keep this as vendor neutral as possible. So I've taken out a lot of the configuration examples that were specific to one vendor. And so everything that I think I've done a pretty good job of making it, everything that I'll be presenting today is true across vendors. There are some slides where I wasn't able to remove certain configuration specific just because I needed to have that to explain some details. So multi-protocol BGP, sometimes people refer to this as multicast BGP. And since that's what we're going to be discussing today, that's really what it applies to for our discussions. Multi-protocol BGP makes it possible for us now to have a variety of prefixes advertised. We can include it in an update now. We can have v4 unicasts, we can have v4 multicast, we can also now have v6 unicast and v6 multicast updates, as well as VPN tag information. You can have a variety of updates within multi-protocol BGP. However, you still need to have PIM to do the actual forwarding of the multicast packets. And the neat thing about multi-protocol BGP, which we'll be going into a fair amount of detail, is that you can use the same rules for BGP as you can with multi-protocol BGP. You can have the same policies and same preferences. So, with multi-protocol BGP now, we can have separate tables. We can have a BGP table used for our unicast prefixes to use for the regular unicast forwarding. And we can have a multicast BGP table because we're receiving multicast prefixes now within these updates. And so we can maintain a separate table, multicast BGP table, that can be used for our controlling our multicast traffic. Do you have to have MBGP to make multicast work across the internet? The answer is no, you don't. You can simply use the unicast regular BGP protocol to do your RPF checking throughout the internet. But for those of us that want to control our multicast traffic, to either have it go a certain path or to assign certain policies to our multicast traffic, you do need to have multicast BGP. Just a very quick reminder of how multicast reverse path forwarding check works, because it is key to understanding this, is that if, let's say that I'm a router and my arms and my head are interfaces. If I get a multicast packet in on my left arm, before I forward it out my other interfaces, I'm going to do a reverse path forwarding check. And I'm going to look in either my multicast BGP table if I have it, or I'll look in my unicast table, and I'll look at the source of that multicast packet, and I'll decide if that left arm that multicast packet came in on, if it's the same interface that I would use to get to that source, then I'll go ahead and accept that packet and send it out the other interfaces. But if the multicast packet comes in through my head, but the unicast routing table is saying to go out my left arm to get to that packet, then the packet will RPF check fail. And that's a good thing. It prevents loops. So all this that we'll be discussing with multicast BGP table just makes it so that you can control your traffic in ways that you want it to be controlled. The way that this works within multi-protocol BGP is that we have address families now. We have address family 1, AFI1 for IPv4, and address family 2 for IPv6. And within each of these address families, we have sub-address families. So if I receive an update, and if it's an AFI1 with a sub-AFI1, that's an IPv4 packet, and it's only used for unicast, so it's going to go into my unicast table for unicast forwarding. If I receive a packet with sub-AFI2, I'll put that into my multicast BGP table so that I can use that for RPF checking. And sub-AFI3 is used for both. It'll go into both tables. Now, all vendors have their way to be able to prefer the packets as they come in for reverse path forwarding. With multicast, we have static routes, static M routes, just like with unicast, so that we can force the RPF check to go out a particular way, and that would have a default distance of 1. But with this multicast BGP table, we can now have that as a preference. And the way that that works is if I receive a multicast BGP update as well as a unicast BGP update, if they both have the same distance, the MBGP update will be preferred, and that will be used for our RPF check. So that's, again, the way that we can control our traffic. By default, we'll do a distance comparison between the tables. With our implementation, you have to configure another keyword, longest match, to make it, if you wanted to have it more unicast-like, for a longest match prefix, you can configure it to do that. There are some scenarios where you may want to have always use the longest match to be your RPF check, if you're sure that that's going to be something that will be able to handle multicast. So there's a capability negotiation that occurs between routers, just as there should be. So if both routers are trying to establish a connection with one another with BGP, if they're both specifying that, yes, I can understand both unicast and multicast updates, I'm multi-protocol BGP aware, then a capability negotiation occurs between these routers and the session's brought up, it's established. Looking at this a little bit more closely, if I receive an update from a BGP peer, if it comes in with an address family of 1, which is for v4, with a sub-AFI of 1, which was for unicast, and go ahead and put that into my unicast BGP table. Now, if I receive another update with a sub-AFI of 2, I'll go ahead and put that in my multicast BGP table for my, again, my RPF checking. And if I receive one with a sub-AFI of 3, then it will go into both. So you may wonder, why would you even bother having, running multicast BGP in an environment where there's a concurrent topology, like your unicast and multicast traffic is going along the same link? Well, one reason would be that you may want to assign different policies to your multicast traffic, and you would subsequently want to advertise those updates to the rest of the world with those policies. So that would be one reason. But probably the more obvious reason that you would want to run multicast BGP is when you would want to have your unicast traffic on one link and your multicast traffic on another link. And so on one link, you can just specify this will be just unicast only. And on your other link, you can specify that it will just be multicast only, sub-AFI 2. So multi-protocol BGP, multicast BGP, now it solves part of the interdomain problem. You can now control your traffic, assign policies to it just like you can with BGP, but we still need to have PIM to do the actual forwarding. MBGP, again, just allows us to control that traffic. So that leads us to the next piece of the puzzle, and that is MSDP, which is required so that we can discover sources out there. MSDP is an amazing beast. It was meant to be a temporary solution until something else came out that would take over. Originally, it was thought that BGMP would be the protocol that would take over to be used as a long-term solution. I'm not sure where BGMP is today. Maybe some of you know. It seems like it's kind of died in the ITF, but what's happened subsequently is the different vendors have optimized MSDP to make it more scalable and to make it better. I'll talk about the amazing spec, but Spec 20 was published this week for MSDP. I don't know if that's a record or not, but it's been just tedious with trying to have agreement on all different rules, and it's just been an amazing process. But MSDP isn't going to be going away, definitely not for V4. We'll get into what will happen with V6 towards the end of this presentation, but it's being used today, it's being used well. If you regularly attend IETF, you'll find a lot of MSDP bashing, but it's being used in production, and most people like it. It's just hard to understand, and that's where we're going to go into some detail. So let's say that we have, which is the case, we have a variety of different domains, and they're all doing their own multicast, they're all enjoying receiving it. They all have their own rendezvous points. But the problem is they don't know sources that exist throughout the internet, like just different, Microsoft and HP, they got their own sources, and other people want to be able to view those. If you're not within their intranet, how are you going to view that? Well, that's where MSDP comes into play. Let's say that in domain E you have a receiver that's wanting to join a particular group. It wants to receive Fashion TV. So it sends a join to that domain E's rendezvous point. In domain A is where the actual source is for this stream. It starts sending out the packets and it registers to the rendezvous point in domain A. As soon as a register is received by that rendezvous point in domain A, if it's configured for MSDP peering with all these other rendezvous points, it will send an MSDP SA update, a source active update. Just letting everybody know in a small packet that this is the source and this is the group. If you ever have a receiver that's interested in this, you know how to get to me, and we'll start forwarding it throughout the internet. That router in domain A is the originating RP. That's an important concept to understand because that's what we do an RPF check against. With regular multicast packets as they come in, we do the RPF check based upon the source. With MSDP, it's a separate RPF check. It's called an MSDP RPF check, and we do it on the originating RP. So that's what domain A's RP is. So the SAs are flooded throughout the internet. There's a variety of rules that have been hard for people to grasp to make it so that these packets don't just get flooded endlessly, since these packets do have an infinite TTL limit. So they would endlessly loop if there wasn't this complex rule. So the SAs do eventually get to domain E. It does have a receiver. It's interested in getting that traffic, so it sends a join. If it's running multi-protocol BGP, it will send the joins throughout the internet that way. And the way that sparse mode works is you cut over to the shortest path tree in domain E, and the receiver is able to happily see the fashion TV models walking along the catwalk. So that is SA forwarding for MSDP. Again, it does contain the not only the source and the group, but it also contains the originating RP address. It will also carry the first multicast packet, which is a hack primarily for SDR. I won't go into the details of that, but it just makes it possible so that SDR can, it's bursty, so it's required. So here we go. For the next 10, 15 minutes or so, I'm going to talk about some rules with MSDP. And this has been difficult. I think I'll present it in a way that will be fairly clear, I hope. It's cause for a lot of confusion for people in trying to implement MSDP, wondering why the packets are getting dropped. But there's really just a few rules here that I think I'll make pretty clear with a variety of illustrations to help you understand how MSDP works within your domain, whether it's just within your own enterprise or as a service provider. There's certain things you need to do to make MSDP successful. So there are primarily 3 rules. It's really 2 rules, and I'll explain why that is. But sometimes you have an MSDP peer within your own domain. Sometimes you have an MSDP peer outside of your domain. And sometimes you have an MSDP peer without being a BGP peer at all. What was decided originally with MSDP is that we were going to have our RPF checking based upon BGP. It's already out there in the internet, and so we'll use BGP as the next hops, and the advertisers of the next hops as our underlying RPF mechanism. So it's very reliant upon BGP. There are a few exceptions, however, and we'll go into detail on these, but when you're peering directly with the originating RP, there's not a chance for a loop, so you'll just skip the RPF check altogether there. If your MSDP peer is a mesh group peer, we'll also skip the RPF check. And if your MSDP peer is your only MSDP peer, there's no chance for a loop, so you'll also skip the RPF check. So let's get into rule 1 on how this works. Your MSDP peer is within your domain. It's an internal BGP peer. The rule with this is, and this is the most strict case within your domain, and there's ways, again, to skip around this, but within your own domain, you ask, the router checks to see if your MSDP peer address equals the BGP peer address. If yes, the RPF check succeeds. If not, it will fail. Let's look at this in detail, and I think I'll make this clear. So router G in AS5 is the originating RP. It has a source. It's registered to it. So router G's address, 172.16.6.1, is the originating RP, and it's going to go ahead and forward out the MSDP SAs to the other RPs that it's peering with. In this case, AS7. It gets flooded down into AS100, and that's where our focus is now. It's AS100. Router A specifically. So router A receives an MSDP SA update coming from router E. So it has a choice now. Am I going to accept this or am I not? Am I going to fail on this to prevent a loop? So what router A does is, okay, my BGP peer address is 172.16.3.1. I received the MSDP peer address. I received the MSDP SA update from a peer address of 172.16.3.1. They match. They're the same. So I will RPF check succeed. It's pretty basic. It's kind of anal, but but it works. We made sure that it has to be the exact address when it's within your domain. Now router E down in AS100 will as it should, forward off that SA also to router D, and router D will forward it on to router A. So router A will get this SA from two different MSDP peers. So the same decision algorithm occurs. In this case, the MSDP peer address, 172.16.4.1, which is router D, is different than the actual BGP peer address that I would use to get back to the originating RP. See, router A in its BGP table, it says, okay, what's the best path to get back to originating RP? Originating RP is router G up there in AS5. So the best path is saying to do that would be to go to 172.16.3.1, which is router E. So they don't match. RPF check fails, and the packet is dropped, as it should be. That's a good thing. Continuing on with Rule 1, a common mistake, and a question in the back.
So if I understand correctly, the RPF check is based on the relative lookup for next hop to the source for the originating RP.
That's exactly right. So the question was, is the RPF check done based upon the next hop? It's actually, and I'm going to get into some newer rules towards the end, but it's actually the advertiser of the next hop in BGP back towards the originating RP. So it's all based upon, we don't care about the actual source in an MSDP RPF check, it's the originating RP. You're exactly right.
And when the initial checks, or the first two checks were checked for, did that then come from somebody whom I'm peered with? Is that, so the address that are compared, is that the loopback, or which address is the one that was compared? Like, let's say you peer on loopbacks, and is that the address that
That's a very good address. That's a very good question, and we're going to address that right now. Because your MSDP peering, it could be on the loopback, it could be on the directly connected, and which one are you going to use? Same with BGP. Well, that's a common mistake, and that was a great segue. Thank you. Is that when a update in this case, we have our BGP peer address is 172.16.3.1. Let's say it's a loopback address. It's not the next hop. Okay, that's fine. My MSDP peer address is 172.16.20.1. Maybe that's another loopback or some other interface on the same router. They're not the same address. So we're going to RPF check fail. It's extremely rigid on in the interdomain side. Even though their addresses are on the same box, they're not using the same address. So that will RPF check fail. So a common problem is if you're using a route reflectors become the advertiser of the next hop. They don't become the next hop, but they become the advertiser of the next hop. So what happens here? Well, same problem as what I mentioned before. And this is a common problem when you're deploying multicast in your domain is when you're using route reflectors. In this case, the BGP peer address is the route reflector, 172.16.1.1. Your MSDP peer address is router E over there. They don't match. So we're going to RPF check fail. So what do you do about that? There's a couple things, and we're going to get into mesh groups, but you can put it into a mesh group, which, as I mentioned earlier, will make it so that you'll skip the RPF check. You can peer to the route reflector. Some people balk at that. They don't have to be peering always with the route reflector, but that's one way to get around it. But it's just important that within your domain that you use the same MSDP peer address as you would for your BGP peer address, and it's a common mistake, and it's just something to be aware of. So now we're getting to another rule. This is really the only other rule that you really need to remember. Within your domain, you've got to peer with the same BGP address. The second rule is when your MSDP peer is an external address. It's outside of your domain. How do we do this RPF check back towards the originating RP? What we do is we look, instead of the advertiser of the next hop back towards originating RP, now we're looking at the next AS in the best path back towards originating RP. So it's not quite as rigid. You don't have to be so concerned about using the same IP address. It just has to be the next AS in the best path back towards originating RP. Let's look at some examples to illustrate this to make it clear. Okay, so same scenario. Router G is the originating RP. The SA is flooded throughout the internet. It gets down to router A and AS100. That's what we're going to be concerning ourselves with. It needs to make a decision as the SA comes in from router E. The decision is, okay, I received the SA from 172.16.3.1. I know that address is an AS3. So for me to be able to accept this packet, my AS3 better be the same, the next AS and the best path back towards originating RP. If it is, I'll accept it. In this case, they are the same, and RPF check succeed. Let's see what happens when it comes away the other way around. AS3 will flood that SA over to AS1, and AS1 will flood that packet down to AS100. Decision process needs to take place. First AS and the best path back towards originating RP is still AS3. That's the preferred route, whether you have it in MBGP or BGP, whatever you're using. But the AS of the MSDP peer is in AS1. They don't match. So the RPF check will fail. So this is our way to make it so that the MSDP SAs will not endlessly loop. Those are really the two rules you need to understand. Just kind of a slide to kind of see what happens. Yes, in the back.
So this is in reference to the previous slide where you have to do an RPF check based on AS path, really, right?
That's right.
So I suppose this would have to be almost always done in software because you have to have AS information for an address.
That's correct. So the question is this is based upon AS path, what the best AS path is back towards originating RP. And that typically, if not always, would need to be in software, and that would be true. So looking at this a little bit further is when you're using your border routers for your MSDP peering, you very quickly, within your own domain, AS100 here, have to very quickly get back to these very rigid internal MSDP peering rules of having to use the same IP address. Because router A in this case becomes the announcer of the next hop, so everybody's got to peer towards that address. But if you peered further into your network, like if router E here, instead of peering with router A, was instead peering with router B, then you would be able to skip all the having to peer with all the exact IP addresses. And I'll illustrate that a little bit more further because that's commonly done. Okay, even though this next rule is listed as Rule 3, it really is basically just an off-take of Rule 2. And that is when your MSDP peer does not equal your BGP peer. It's the same exact scenario where you have to just find the next AS and the best path back towards originating RP. And just hang on with me for like another 5 minutes. We're almost out of this tedious RPF checking, but it's just kind of important to understand. If you understand this, you're probably the only 30 or so people on the planet that understand it, and you make yourselves extremely valuable to people you work with. In this time of day, that's kind of important, unfortunately. So let's look at that rule. Router A gets a SA from router E. It's not MBGP peering with router E, it's peering with router B. So it's very reliant upon BGP, so how's this going to work? But it's the same way. Router A's table will just show that router E is in AS3, which is the best path back towards originating RP. And the AS of the MSDP peer is in AS3. So we're going to RPF check succeed. And when it comes around the other way, we will RPF check fail for the same reason as in Rule 2. It just happens that we don't have a direct MBGP peering with them. So the nice thing about this, and this is what's commonly used in service providers today, is they have a group of rendezvous points within the core of the network. They're running Anycast RP, and I'll discuss that in detail in a few slides. And those routers are the routers that are peering with all their customers. Instead of using all the border routers to MSDP peer with all their customers, they just use this subset of routers, 10 or so, or 10 or under RPs that are MSDP peering. And the nice thing about that is since those are external MSDP peerings, we're just using the next AS and the best path back towards originating RP rule. We don't have to be so concerned about the actual IP address as with internal MSDP peering. And router E and router F would be in a mesh group, so it would be skipping the RPF check altogether, and you'll understand that if you don't already in more detail. But this is a typical deployment scenario. And AS RPF check works the same as I've previously discussed. All right, so mesh groups. Mesh groups were created to cut down on SA flooding. And this is an intra-domain solution. So a lot of providers use this as well as enterprises. If you have a lot of MSDP peering going on, they are flooding the SAs to one another. Eventually they'll stop, but they are going to be flooding, as they should, to all their MSDP peers. To cut down on that, you can put them all in a mesh group. And what happens within a mesh group is if you receive an SA from a mesh group peer, you will not forward it out to any other mesh group peer. You'll forward it out to other peers you may have outside the mesh group, but not to any others within it. So it cuts down on the flooding. And the reason that you don't have to send it out to other mesh group peers is because you know that they've already received it. Because within a mesh group, you have to be fully meshed. So looking at it in this scenario, if router 4 in this case is outside of the mesh group, it sends an SA to router 2. Router 2 has mesh group peers router 1 and router 3. There could be 20 or so of these peers, but in this case there's just 3 to illustrate it simply. Router 2 will forward those SAs to its MSDP mesh group peers, but router 1 and router 3 will not forward them to one another because they know that they've already received them. It cuts down on the SA flooding. But router 3 will send it off to another MSDP peer outside of the mesh group. And there's some examples, configuration examples that you can easily apply to other vendors, but it just kind of illustrates how that works. So as I mentioned before, we're at draft spec 20. And it's just been an amazing process of trying to get agreement and just to get the darn thing closed. And it looks like as of this week, it will be an experimental RFC. Don't have a number yet, but it looks like we are finally done. What we did is we just basically took out a ton of stuff and just tried to find a common denominator that we can all agree upon, and made a lot of mays instead of musts. And so you'll have to take a look at that spec. It's pretty efficient. I've subsequently submitted a multicast, an MSDP BCP, best common practice, which discusses a lot of the things which we are discussing today to help understand how you would deploy it. It came up on the mailing list that it's just really difficult to deploy MSDP. That's one of the reasons we hate it. So we need to have some sort of a best common practice. And so that's been submitted. David Meyer and John Myler are on that as well. They gave it their blessing, so that's good. So you can look those up to take a look at.
Back on your on the mesh. I'm sorry, I should have asked.
That's fine. Yeah, go ahead.
What's the motivation to eliminating the other routers communicating their SAs? Is it just for traffic, or is there some other complexity reason?
Right. So the question is in this. Back on slide 38, router 1 and router 3, being that they're in the mesh group peering, they aren't going to send the SAs to each other. And the whole motivation, it's pretty simple, is just what you just said, is just to cut down on SAs. Let's say you had 50 MSDP peers. If router 2 received that SA and it had to send it off to, it would send it off to all its mesh group MSDP peers. They would subsequently send it to all their other peers, and they would send it to all their peers. So it's scaling is what it is exactly. So if you have a lot of MSDP peers, it works good. If you don't, then it's not that critical. However, it is used in Anycast RPs, and we'll discuss that also. Good question. All right, so this is the first time that I've presented this portion of the presentation. All these RPF rules that I've discussed that are presented to you. In the latest draft, there's been some additions to MSDP to try to make things a little bit better. And I would assume most implementations now have implemented these new options, these new rules. And so in latest code, primarily not what's out there today. What's out there today is what I've just discussed. But with newer code that has the latest draft, is compliant with the latest draft, there's some new things that you need to be aware of. One of them is that we've taken out the requirement of always having to use BGP to do your RPF check. Now, if there is no BGP, you can fall to an IGP, OSPF, ISIS, whatever, to do your RPF check. And that's kind of cool. We can now accept SAs from a BGP next hop, not just the advertiser of the next hop, but the next hop itself. And I'll illustrate each of these. And there's also the ability now with the latest draft to accept SAs from the closest peer along the path not just the next AS in the best path back towards originating RP, but any AS that's the closest one in the next path back towards originating RP. So I'll talk about each of them briefly, and then we'll move on out of the nightmare of RPF checking. So let's say again that you don't have BGP, but you are running OSPF, and you want to be able to use that for your RPF check now. And now you can get to that. So in this environment, we're not running BGP. Router A gets an update SA from router B. They'll just look in its unicast routing table. It does have a route back towards originating RP, which is 2.1.1.1. The MSDP peer is also 3.1.1.1. And so they match, and the RPF check is successful. We'll forward that on to other MSDP peer. We can also use, as part of this IGP check, the advertiser of the next hop. Like OSPF and ISIS, where you have a router ID, you have that. RIP doesn't have that, it just has the next hop. But with protocols like OSPF, you do have a router ID, so you can use that if you wish, if you aren't required just to use the next hop. So let's say 4.1.1.1 is a loopback on router B. We can peer with that. The next hop towards the originating RP is 3.1.1.1, so normally we'd fail, but we do have the advertiser to originating RP, which is 4.1.1.1, so we're all happy. RPF check succeeds. So just be aware of that. That's something that's, if it's a requirement of yours that you want to be able to use an IGP, then just be aware that there's code out there now in EFT form that you can use. We can also now accept SAs from the next hop, not just the advertiser next hop, and in fact, next hop is actually preferred. So in this case, in this route reflector scenario, router E is the next hop towards the next hop back towards originating RP. The MSDP peer address is 172.16.3.1, but the BGP next hop is 172.16.3.1. So the route reflector is the advertiser next hop. So normally it would fail, as I illustrated before, but the next hop is, if you're using like next hop self, is the next hop, and we'll use that now for RPF check. Just put that in your bag of tricks and just be aware of that. And yes?
Question about that last.
Yes.
I'm not sure what you meant about the status of this. Is this current practice and the standards are lagging behind, or is this still something we're thinking about?
It's implementations lagging behind the spec. So implementations are now becoming spec compliant, as we've quickly tried to bring the spec home into RFC status, which it looks like we've done now. And so this option is now available to use if you need to. But if you were going to implement with existing code today, probably on all vendors, I'm guessing, not only ours, the rules that I've mentioned at the beginning is what you would need to be aware of. So it's going to be some time before the new code. You know how router code is. That you don't obviously usually in your service provider space, usually you use brand new code out there. So well, maybe you live on the edge. I don't know. So the last thing is to be aware of is that in this case, AS1 receives an SA from AS3. In the existing rules, if the first AS in the next path back towards originating RP is not your MSDP peer, which would be router 2, then it would fail. Because router 2 is AS2 is the next AS in the best path back towards originating RP, so you'd have to MSDP peer with AS2. Now we've relaxed that a bit, so just say, look at the AS path, just look at the closest AS, and just if that's good, then fine. Let's just use that one, and be on our way. So there we are. That's MSDP. We're doing pretty good for time. So we've discussed the two protocols now that are being used to make multicast work across the internet. If you have your own company and you want to start forwarding multicast traffic out to the world, you need to talk to your provider and say, okay, we need to start setting up some peering, and I need to get an MSDP peering set up with you. And we'll go over some examples, different deployment scenarios of how you'd get this to work. Let's first go into Anycast RP. So most of you probably are somewhat familiar with Anycast RPs. Anycast RP is a solution that was created to be able to have redundancy and load sharing. With multicast, you can have one rendezvous point for a particular group. It'd sure be nice to be able to have a variety of rendezvous points to be able to use for backup, for load sharing and redundancy. And that's what Anycast RP function does, is it allows you to assign, usually it's a loopback interface on several rendezvous points, let's say two or three or whatever, and they have the same exact IP address, /32, and your sources and receivers will be directed just using unicast routing towards the nearest rendezvous point. And if that one fails, they'll just be directed to the next nearest one. It's kind of cool, and we'll look at an example of how exactly that works. It's very fast convergence, just depends upon your unicast routing that you're using. So let's take a look at an example. We have East Coast and West Coast rendezvous points. And they have an MSDP peering with one another. They both have the same Anycast RP address, 10.1.1.1. So the receivers on the West Coast send their joins for a particular group, and those joins are directed towards the nearest RP, which is on the West Coast. Same thing happens for the receivers on the East Coast. A source fires up on the West Coast, and the receivers on the West Coast receive that traffic because they're interested in receiving it. But the receivers on the East Coast have no clue on that source existence because they're not using the same actual rendezvous point. So that's why MSDP is needed. The West Coast rendezvous point will send an SA over to the East Coast, letting that router know that it has an active source, and if it has a receivers interested, go ahead and join towards the source, which it does, and the receivers get the packets, and if there's a source on the East Coast, the same process occurs. So let's say that router A dies, heaven forbid. So what happens? Well, the receivers continue to get the traffic because typically with sparse mode, you're going to cut over to the shortest path tree and the rendezvous point can die and you don't care. You're getting the traffic natively. For any new sources, they're going to be directed over to the other rendezvous point, just as quickly as unicast routing can direct it over to the other rendezvous point. So it's very quick failover, it's very seamless, and it works awesome. This is where I had to just put in configuration commands that I was familiar with just to kind of make it clear. All your routers within, yes, question?
So on the previous example, Anycast SA or Anycast setup between two RPs and one sending and SA to the other, would the receiving RP process it? Because the advertising router ID would be the same as itself? Yeah,
very good question. We'll discuss that right now. I'll answer your question. That was good. The question is that since they're using the same IP address, would they accept the SA from one another? If they receive the SA from the same IP address as itself, no, it wouldn't. So that's why it's important to use a different address, and I'll illustrate that right here. So all the routers in the internet within a domain, and this is commonly done, is in a service provider space, typically we would recommend using static configuration for your RPs. So they're all configured to statically point to the one Anycast RP address, in this case 10.0.0.1, which is your loopback interface on both rendezvous point 1 and 2. Loopbacks 0 on both routers, however, are used for their MSDP peering. There's a separate loopback interfaces, and they need to be used to use your MSDP peering to use those addresses, because as was mentioned, if you were using your Anycast RP address as your MSDP peering address, you would fail, because if you receive an SA from a peer that's the same as you, that would be a loop, so you're gonna drop it. So your Anycast RP address is just used for Anycast RPs. That's where all your routers in your net point to. Separately, you have a loopback interface which you use for all your MSDP peering. All right. Let's move to a multicast exchange environment. We have multicast exchanges throughout the world. There's the Ames multicast exchange at NASA, which I'm familiar with mostly, as well as the Palo Alto exchange. What they do is all these tier 1 providers are peering with one another using MBGP and MSDP so that they can have the sources known to them as well. And typically you'll have just a regular switch, everybody connecting up to a switch. What is getting more common nowadays, like at StarTap in Chicago, I believe it is, where they use point-to-point VLANs instead for a more deterministic approach to your RPF checking. But that's the way that it works today, is just as it is with Unicast, as you have your multicast exchanges sharing SAs and MBGP peering one with another. For security with MSDP, we do have a recommended filter list. And there's a draft out now. This one from Bill Nicholas is actually timed out, and I pinged him, and he's going to resurrect that one, and it's going to be a note too, I guess. But there's certain groups out there that, particularly on the application side, that they've chosen for their application global multicast addresses. And so that's kind of a bummer for the multicast, the interdomain space, because when they're setting these, the local RP will go ahead and send out SAs about these applications that are meant to be just domain local. So the whole internet's hearing about these applications, which they don't need to be hearing about. So as we find them, and as well as other well-known groups, we add those to the list of recommended filtering, so that we prevent at the edge unnecessary SAs to be flooded throughout the internet. While we're on the topic of MSDP and security, there's also a recommendation to use a SA limit. All vendors that have implemented MSDP will have an SA limit. Right now, the SA count is typically hovering around 2,500 SAs. So people usually either choose 3,000 for an MSDP SA limit, or maybe 5,000, just to give kind of a room. But it's possible, and it's happened in the past, and things have gotten a lot better nowadays, but it's possible that there could just be a huge flood. You get 30,000 SAs, and that SA limit will make it so that won't cause a problem. All right, we're going to now quickly go through a variety of scenarios, of deployment scenarios with multicast across domains. Let's first say that you have a customer who's interested in, or you're the customer and you're interested in sourcing multicast or just receiving multicast from the internet. You don't have your own RP, you don't want to maintain your own RP, you just want to use the service provider's rendezvous point, and the service provider said, fine, just go ahead and use ours. So what do? Well, you point to their rendezvous point, and so any sources on your domain or any receivers that send a join, that will all be forwarded off to their rendezvous point. This transit provider over here in AS109, it has its dual rendezvous points, and you're pointing as a customer to one of those. And so the provider will also be pointing to its own rendezvous points. And both the customer and the provider will be doing some filtering. They'll do the filtering for BSR border. And the important thing on that is I had a nightmare one time working with a provider where a customer was using BSR, which is an auto RP discovery program, and that was getting flooded into the provider's network. And so it was wreaking havoc on its own RPs, and we didn't know what the heck was going on. And the BSR border command wasn't being implemented, which will stop it at its tracks. It won't go in or out when that border command is configured. So that's an important one to use. A boundary command is also recommended to use. You create an access list, and you filter out any multicast group ranges that you want. With our static assignments, it's important to have the override, and this is another thing that we were missing with this provider, is we were missing the override command. When you have a static RP assignment and you receive a dynamically learned RP, whether it's through auto RP or BSR, that will be preferred unless you have override on your static command. If you have override on your static command, the static command will always be the one chosen for your RP. That's critical to use. If you look at your RP mapping, you'll show the RP address of the provider's RP. There's no MSDP running here. You're not running your own RP at your customer site, so there's no need to have it. So there's no RPF check. The Multicast RPF check, once the packets do come into this customer site, it will just use if it's running BGP, it will use that. If it's using a default route, it will use that as its regular Multicast RPF check. And the transit provider will have a static route for your subnet and advertise that out to the rest of the world, both via Unicast and Multicast, because the rest of the world may assign policies to your updates. So that's why they will want to have yours be known to the rest of the world via MBGP. All right, so let's say the provider tells the customer, you know what, can you maintain your own RP already? Or it's just simpler, just use your own RP. Or maybe the customer wants to maintain their own RP. They want to have more control over that. So they do so. They create their own RP, and they're using Multicast just fine within their own domain, and they want to be able to advertise their sources out to the rest of the world or receive information out from the rest of the world. So the same filtering would apply, but now we're running MSDP, because that's the only way that we're going to be able to learn sources that exist out there in the world, since we have our own RP now, our own island. We need to know what the other islands are doing. So we'll MSDP peer with one another. We'll have a filter list to make sure that we don't get hammered by unnecessary traffic. We'll have our MSDP RPF check. If it's just a telesite customer with one MSDP peering, then the RPF check will just be skipped, because there's no need for there's not a looping problem. It's just one MSDP peer. The transit provider will be peering with you. Typically, they will be peering with the customer's originating RP. So there's no need to do an RPF check on that either, because there's no chance for a looping. And then the Multicast RPF check will just be done as before. When the packets do start flowing in, you'll just use your Unicast routing table to do the RPF check. So this is the scenario of how we're doing Multicast here next few days here at NANOG. The University of Utah has provided the network scenario. We have an MBGP peering with Sprint. They're multi-homed. They're peering with internet. They got linked to internet too as well. But just to make it as simple as possible, we have a MBGP peering with a border router within Sprint. We have an MSDP peering with one of the several RPs within the Sprint's backbone. We have the filters set up. The rendezvous point, the Sprint's backbone is running this Anycast RP as a mesh group going on. These RPs within the Sprint backbone have MSDP peerings with all the other customers, in addition to NANOG. And the MSDP RPF check is done just as we've discussed. The NANOG router will just use it would have multiple MSDP peerings because it has other providers out there. So we'll just use whatever the MBGP route would take it to get there. It will use the Sprint's AS and the next best path back towards originating RP, if that does happen to be the next AS and the best path back towards originating RP. And then Sprint's MSDP peering with NANOG. And the NANOG AS here would be the next AS and the best path back towards originating RP, since NANOG RP is the originating RP. And the Multicast RPF check is yes, question in the back.
I was curious about the command, IP, MSDP peer, and then connect source.
Which we're not supposed to talk about, but yeah, go ahead. I'm just joking. No, I'm just joking. It's vendor specific, so just go. Who cares?
So on the RP and the transit AS, what does that convey? What information does that convey? Because that router is not going to know about the connect source address, right? It's a peering router, like a BGP peering router.
The connect source address makes it so that you can control which address is used in the MSDP update. So in this case, at NANOG, it's peering with 3.3.3.3, which is a Sprint router, and it needs to know about that address via BGP or MBGP.
Now, I was curious about POS 0/0 on the RP and Sprint router. Like, what does that?
That's significant. That's just specifying an IP address. You could just as well specify an IP address.
Well, it's just so happened on that RP router, it's got an interface.
That's exactly right. That's right.
I thought you were somehow referring to the Sprint peering router.
Oh, I see. That okay. Yeah. So there was a little confusion on the pause. That's just no. That's like with the Unicast. You just can specify instead of actually specifying an IP address, you just specify an interface. Yeah. I'll have to try to make that clear next time. So then the Multicast RPF check just uses, BGP, MBGP if it's there. Hopefully it is. And away you go. Another scenario is where you are dual homed. One provider may be multicast only. Another provider may be unicast only. You want to break it out that way. So you'll obviously just be MSDP peering with the multicast only provider and not the unicast only. So you'll just be setting up filters with that transit provider. The MSDP RPF check, again, you just have one MSDP peering, so it's a no-brainer. There's no check necessary. If there was, you would just use MBGP and decide which path you should accept. And the Multicast RPF check is done similarly with BGP. And then lastly, which is most ideal, is you have multiple providers, both providing multicast and unicast transit. You're peering with both MSDP as well as MBGP, setting up filters with both. They're advertising your networks because they're learning about your networks via an MBGP. And you'll just choose whatever the AS is, that's the next best path back towards originating RP. That's what will be used to do the RPF, the winning of the RPF check for MSDP. And same is true for the multicast packets, which is, again, a different RPF check. Once they start coming in, we'll just, whatever's the best path, that will be the one that will be chosen for the RPF check. So there's a variety of examples. I kind of flew through those, but hopefully that gives you an idea of kind of the deployment options, and we'll continue to talk about some more here. I've got to fly a little bit, but we're not doing too bad with time. GLOP. You may ask, with Unicast, you have addresses assigned by IANA. With Multicast, that's not the case. It's kind of a free-for-all. You've got all this Multicast group address range, and what do you do? So you could pick. Some people could be picking the same group address for their multicast sources, and there could be a conflict. And that's true. That could be the case. A concept of GLOP was created, which has gone from the concept stage to the implementation stage. I don't think GLOP stands for anything. It's just an acronym, I believe, that David Meyer came up with. And it's a temporary allocation of 233/8. And again, I say temporary. MSDP was temporary, and it's going forever, so maybe this will last longer than we plan. But it's just a way to allocate. If you have an AS, you can inject that AS into 233/8 and come up with your own /24 used for your multicast groups. The way you figure it out is just write it out in binary if you want, or hex, and map the high order octet to the second octet of the 233/8 address, and the lower order octet to the third octet, and you get your address. All these slides should be posted, by the way, on the site. So are you viewing them? Or? Yeah, okay, cool. All right, so you guys have them, so you can review this later if it's confusing at all. But the easiest way to do it is just to go to a website from our friends at University of Oregon, plop in your AS, and it will tell you what your /24 is for use. And again, that's the recommendation here. There's been a lot of different proposals in V4 for more dynamic allocation of addresses. Nothing has stuck yet, and so we'll wait and see if anything changes with that. Any questions before I move on to the last 3 sections here? We've got about a half hour. All right.
How long is the SA information kept on the receiving router?
On a router? It's probably vendor specific. Ours is 6 minutes. It'll stay in the cache and then time out if it's not updated. Once a minute, we send out the contents of our SA cache. It was specified in the spec that you must cache the SA. So.
And if you send a new SA, let's say a new receiver came out, I noticed that in every SA you list the rest of the receivers that you know about, right? On the slides, it seemed like, or alluded to that. Is that not the case?
Well, you're not concerned about the receivers. You're just concerned about the source. So, yeah, okay, sources. So yeah, any new register that you receive from a source, you're going to go ahead and send out a new SA.
And that SA will contain all the other sources that you know about, right? Or is it just a new source?
It will be the new. It'll be an SA for that new source, because otherwise you'd be flooding all the time. So once a minute you flood the entire contents of your SA cache. If a new SA comes in within that, you're going to flood that. So that.
I must have misread it. I think it was like earlier on that maybe I must have misread it.
All right.
So the question was, if that is the case, then would you still send a 1 minute? I guess that's.
Yeah, you still send it. At least for us, it's a 1 minute deal. But again, that's vendor specific. I don't know how other vendors do that. Yeah, right. So source specific multicast. It's a great idea. It's something that would have been awesome if we come up with this years ago. We would have been able to avoid all the rendezvous point mechanisms altogether. With the advent of IGMP version 3, hosts can now specify the actual source that they want to receive. With IGMP version 1, hosts send a report to the local router saying, okay, this is the group that I want to receive. You can send me any source for that group. It's a star, comma G, just any sources for this group. In IGMP version 2, it was the same thing, but the enhancement is that when a host left a group, it would actually send a leave message to let the router know that I'm gone. So you can send out and you can quickly prune me off. Or in version 1, it would take several minutes for it actually to stop forwarding onto that LAN. With version 3, the hosts, again, can now specify the source and the group. I don't want to just receive any source. There could be 100 sources for this group, and I have to receive them all. I just want this particular source. Very cool. Source-specific multicast on the routers make it possible that when we receive such an IGMP version 3 join, we already know the source. We don't have to go through this whole process of trying to find out, sending the packet to the rendezvous point, the receiver's joins are sent to the rendezvous point, we cut over to the shortest path tree. We already know what the source is. We can immediately cut over to the shortest path tree towards to the source. It's very cool. The last hop router sends the joins towards the source. It definitely simplifies address allocation if you think about it. If the two different companies choose the same group, 224.1.1.1, who cares? Because they're both sourcing it from their own unique source. And since the host is now specifying both the source and the group, it definitely solves that. It definitely simplifies that problem. There's a variety of RFCs out there that describe each of the different versions of IGMP, which we've discussed. Version 3 is more and more prevalent now in the stacks of various hosts. We're just now trying to push to get more and more applications that are SSM or IGMP version 3 aware, so that we can start getting this thing to take off in the interdomain space. Because if there's not rendezvous points needed, then it eliminates the need to even have MSDP. You don't need to have the SA deal that we've all been talking about if SSM is used. SSM is being used today. It's just not widely used. As maybe, hopefully, as more and more applications get developed, it will be used more prevalently. So the way that this works is a source is firing off its multicast content. A receiver learns of this source and group through some out-of-band mechanism. Network administrators are cheering because we don't have to deal with having to have the rendezvous points and everything, have the network take care of it. We're just letting the receivers take care of figuring out how they're going to get the source and the group advertised either via email or web server or whatever. So the receiver learns what that source and group is. It sends an IGMP version 3 S, G join to its local router. That local router is running SSM, so it recognizes that and immediately sends a join towards the source because it knows what the source IP address is. Traffic begins to flow, and those of us in the multicast development group are out of a job because this is extremely simple. This is awesome. And we hope it goes nuts. These are just different drafts and whatnot that specify where SSM is and IGMP v3 is. And it's supported in a variety of router vendor OSs. We do maintain a list of stacks.
So it requires IGMP v3, right?
IGMP v3, that's right.
How widely available is that in the
in the appropriate switches. It is getting there. Yeah. The question was, is V3 now widely deployed, widely supported in vendor switches? And the answer is yes and no. It is getting there. There are certain, like with us, for instance, it makes sense to concentrate on certain switches and make them V3 aware, and depending upon customer feedback, others may not be included in that. The answer is yes. I don't know if you're running code right now that supports that, but you could. Okay, so this is just a summary. It is also just another thought for security. It also will help prevent certain types of denial of service attacks. If I'm receiving a stream, even if it's in my own domain, let's say that I'm at my desk and I'm receiving a corporate broadcast from the company CEO, and it's being broadcast out on 224.1.1.1. If I'm not running SSM and using V3, then some malicious coworker could be in his cube, taking a video of his own head doing, who knows what, and sending to that same group and jamming that content. So I could be receiving both, and it could be all messed up because I haven't specified which source I wanted, just any source for that group. So that's one of the neat things about SSM, is that you've requested a certain source and group, so it'd be much more difficult to spoof both.
Would you run SSM with, let's say, PIM, or do you have to have one or the other?
Yeah, the question is, can you run SSM with PIM? Well, that's a good point, because SSM is PIM. There's PIM sparse mode, there's PIM dense mode, which we don't talk about anymore, really. It's kind of old school. And there's bidirectional PIM, there's source specific multicast PIM. There are different types of modes that, yes, can be used in different parts of your network. So if you were currently using rendezvous points, which you typically would be, and you wanted to start introducing SSM, then you just mainly, at first, just need to upgrade your border routers, not the border routers, your last hop routers, the routers closest to the receivers, because they need to be able to understand the V3 joins. And since SSM is the 232/8 range, you can just specify that this is my range that I'll be using only for SSM. And then in the long term, you can, if you wish, you can just open up that range to not only include 232, but for all your groups if you wish. So that would be that is something that's commonly done.
Have you got any studies? I mean, if you're doing SSM and you have more than one source, obviously you can have multiple SSMs that have the effect of having ASM. Have you done any studies of what kind of numbers that starts to make sense to go back to ASM? I mean, if you have how many sources in a group?
So the question is, has there been any studies done or testing that has to do with what makes sense when, depending upon whether you want to use SSM or sparse mode or any other mode for that matter? I think that there's actually been some scalability numbers done, but I don't know what that is. But SSM is designed for one-to-many, because it's one.
It would work for few-to-many without much trouble, but it's at what point is the few?
Yeah, at what point is the one-to-many, the few-to-many, and the many-to-many? What point? That's an excellent question. I don't think we have really good answer for that. It's just kind of depending upon your preference. A lot of people that have many-to-many, that's where they're going to be going to bidirectional PIM. And so there's a lot of different solutions for different environments. Interdomain multicast is primarily a one-to-many situation, so SSM is ideal. But it probably is not a bad idea to try to come up with some sort of a study on what makes sense number-wise. Good question. All right, so we've got about 20 minutes to discuss these last two. I think we'll make it. So more and more now, there are providers using multicast MPLS VPNs, and up until now, only Unicast has been supported in such a MPLS environment. And service providers were coming to router vendors saying, hey, I've got these customers who we have started implementing MPLS VPNs, and they want to now start running their multicast traffic over this environment. And there's no switching of multicast packets within the MPLS VPN environment. It's only unicast packets. There's no affixing a label to a multicast packet. So what are we going to do about that? We need to come up with some sort of a solution. Well, the workaround up until recently has been just to create a bunch of point-to-point GRE tunnels between all the CEs, which is, if you have a lot of CEs, can be an administrative nightmare. And it's just not scalable. But that's what you would do. And the service providers and the customers have come to us and said, okay, so whatever your solution you come up with to make this better, instead of all these point-to-point tunnels, it needs to be a solution where the provider can use whatever PIM mode he wants, SSM, bidirectional PIM, or sparse mode, whatever, and the customer should be able to have their own mode as well. They need to be independent, not dependent upon one another. So, okay, we take that and we'll make the implementation support any PIM operating mode in customer and provider networks. So our implementation, as well as other implementations, are based upon multicast domains specified in the Rosen draft. And it does just this, and that is that you've got your provider network and you get your customer network. And what we do is when a multicast packet comes in from a customer VPN, we'll take that multicast packet and encapsulate it in another multicast packet, forward it across our network, decapsulate it on the far end side, and send it off on its merry way in its original multicast source mode. So it's what the solution is. It's a dynamic mechanism for creating tunnels between the different PEs per customer, and I'm going to illustrate it as we go along here. I think it will make sense on how this works. It's being used today in a variety of provider networks. So from a customer's high point of view, what they have is they have their own independent VPN for both unicast and multicast. They have their own color, and it's being forwarded. From the provider's perspective, what they've done is they've said, okay, for blue customer, I'm going to use a particular group address, 239.1.1.1 for the blue customer, for instance. So again, when multicast packets come in from the blue VPN and it wants to transit my MPLS VPN core, I will encapsulate it in 239.1.1.1, which will be that address will only be used for the blue customer, and that will be sent to the other PEs that lead to that customer's remote locations. And then for other customers, we'll use a different group address range for all those multicast packets. So let's take a look at a little bit more detail on exactly what's going on with multicast VPNs. So a receiver joins a particular group, and it's the PIM packet, the PIM join is sent from the CE off to the PE. That PE router gets that join, and it sends that packet to a destination address of 239.1.1.1. It encapsulates the customer's packet, multicast packet, and creates a new multicast destination address, which goes to the other PEs within the VPN. The PE that leads to the source will decapsulate that join, send it off towards the router that leads to the source. The multicast data would begin to flow. The PE router that is connected to that source will encapsulate that multicast packet. The PE router will become the source IP address. Again, we have a new destination multicast group address, 239.1.1.1. They'll be sent to all the PEs. The PE that leads to receivers will decapsulate it and send it on its way, and the receiver gets the packet and it's able to view Fashion TV. The receiver's all happy. So if there's any new sources that come up, they will also be encapsulated in that same group address. So one benefit of this is that it definitely reduces state for the P routers. P routers they're just going to know one group address range, one group address for that they'll have to forward on. So that's one of the advantages. Disadvantage, it can result in wasted bandwidth. There are PEs that don't lead to receivers, but they're getting the data anyway. That's one of the problems. And the solution, and this is something that is where the interoperability stops. We could, between vendors, use the default MDT and everything would work just fine. But beyond that, it's not specified exactly what to do. And one of the solutions that you could do, that we've done, is to use a separate data MDT for high rate sources. So what that would mean is that when the multicast traffic is forwarding across this default multicast distribution tree, MDT, it would exceed a certain configurable threshold on the PE router that's connected to the high rate source. The PE router would send a control packet to all the other PE routers, signaling those routers that if you have receivers that are interested in a particular source, please send a join to me, and we're going to use a new group, 239.2.2.1. So the PE routers that have receivers will send a join to this new group now. And the data MDT is built using this new group. And the traffic begins flowing along this new tree. You still have the existing default MDT for any new sources that come up, and all the control packets, they still occur on the default MDT, but you can now cut over. And again, that's about as specific as I want to get, because that's a solution that we do, and you may just want to ask your vendor what solution, if any, that they may have for that. They may decide that it's maybe just not, it may not be necessary. You may just want to stick on the default MDT. So that's kind of just this is just kind of the picture of how it all ends up with your different VPNs and setting up your default MDT, and it works pretty good. Any questions on that before we move on to V6? Yes, in the back.
I guess in the last two slides, it goes back to increase the state on the DP routers, because now you have to keep track of which receivers want to listen to what source, right? As opposed to just keeping information about which tunnel to which site.
That's right. So one of the potential drawbacks of cutting over to a data MDT is that now the PE routers have to maintain more state for new groups, and that's true. So you would just need to decide whether, and that with us is configurable, whether you'd want to ever even cut over to the data MDT. I would think that for efficiency's sake, in many cases would be preferred to cut over to a data MDT, but good point, maybe not always. All right, V6, lastly, and this is kind of the fun part, because this is all new stuff. We have a new multicast address range, and it's FF/8, excuse me. And there's a lot of neat things about V6 addresses. You've got 4 scope bits that you can specify whether this address is link local or global or regional or whatever, so that you can, on your routers, set up your filtering so that, okay, no address that's is global will pass my interface. So it's much it's easier to do your boundaries. With V4 today, we have to set up a boundary command and specify the group address range that we want to bound. Just a little brief history. I'll try to make it brief on where Multicast V6 stands. With Unicast V6, it's been around for several years now. A tunnel topology in the 6-bone. And at the last IETF, it was decided to decommission the 6-bone and to go native. And there was a specific date that was chosen. Some of you may have been there at that working group. And we're following suit. We really want to aggressively make it so that we've learned from previous experience with the old M-bone, which in some ways we're still kind of fighting with the tunnel topology, is to kind of go native as quickly as possible. So what Renator out in Europe did is they created a M6 multicast 6-bone. So it is a tunnel topology for a lot of testing, and a lot of people are involved in that. A fair amount of applications have been created to work on V6, and it's there today. And again, we knew that we wanted to aggressively get out of that mode, however, and go to a more native approach. A lot of people have created native networks as we vendors have come up with implementations. And so there's a lot of different environments now, like for instance NASA, their production network is V6 capable for multicast, and so there's a lot of these little different islands, people of companies that have now gone to a native mode. And there is a new network that was created, a new environment that was to be able to support these native implementations, and that is 6net. Renator, who maintained this M6 bone, is an active participant in the 6net. And this is a network of a native solution where we're able to test and people are able to natively get a solution for multicast and unicast for that matter. And so we're in this mode now where we're just really trying to push people to go natively with V6 as quickly as possible. There's a variety of stacks. Kame, I believe, was one of the first ones, if not the first one. There's a variety of applications now that support V6 for multicast. There are some obvious differences between V6 and V4 multicast. One of the differences to be aware of, if you're not familiar with the terms, is with V4, I've talked about IGMP, Internet Group Management Protocol, where the hosts send the reports. In V6, it's referred to as MLD, Multicast Listener Discovery. And there isn't even a version of MLD that's equivalent to IGMP version 1. Well, MLD version 1 is equivalent to IGMP version 2, and MLD version 2 is equivalent to IGMP version 3. So I put that slide in there because you may have to go back and look at that one. Again, I've mentioned the scope identifier. There's the 4 scope bits, which make it a little bit easier to filter on the edges. And the interesting thing, and this is kind of what we're going to get into, is the whole idea of how we are going to have an interdomain solution with V6, and that's still in debate. People in IETF are aggressively trying to make it so MSDP isn't even allowed to be implemented within V6. They don't want to have to deal with all these different rules that I've mentioned and the SA flooding and forwarding throughout the internet. Some of us think that it may be unavoidable, at least at the beginning, so we can get things to work quickly. We shall see. One of the solutions is to have global RPs. Everybody's dependent upon a certain RP. A solution that was brought up for V4 and MSDP replaced that because service providers didn't want to have to rely on an RP of somebody else, and it makes it so you're reliant upon other domains. I'm going to, in a few slides here, discuss some different options that we have available to us, and we'll end on that. So RPF with V6 multicast is the same as with V4 multicast. You just use your, it's protocol independent, and you just use your unicast routing table. MBGP supports V6 address families, and we can use those for RPF. There are some definitions to be aware of. A PIM domain is a topology served by a common RP. So if we have one big fat happy PIM domain within the internet, we have a bunch of different routing domains, of course, that's based upon the AS, but one big PIM domain. Is that what we want? Well, time will tell. And I've mentioned scopes and boundaries, so I'll pass on that one. So this is our last 2 slides here. So I think we've done pretty good. So here's our interdomain solutions. I can see 3 solutions that are available to us to make this work with V6. And we need your feedback on what you'd prefer. Because the IETF sometimes is kind of it's our own academic sometimes world, and we need real customer feedback. So we have SSM. There's no need for rendezvous points. It's extremely simple to have the receivers learn of the sources and groups and just fire off the joins towards the source, and it's extremely simple. Some people really support this, saying, you know what, let's just have SSM only. Start it right from the very beginning. Let's just have SSM only in V6. Yep. I hear a yep back there. Okay, so that's something that a lot of people want to see happen. Another solution would be, okay, well, some people feel that we just really can't get away from any source multicast. It's just, it's going to be a long time between all of our host stacks are upgraded to be able to support v3 and all the routers, et cetera. So we want to be able to use v6 Multicast today. We need to have a solution. Well, if that's the case, then today we need to have a MSDP-like solution, or just use MSDP to make it so that we can learn of sources and other PIM domains. And as we've discussed, we have all our different RPF rules, et cetera, but the receiver will be able to receive the packets from the source. So that's another option that's available that's still being debated. And then lastly is the concept of, again, having one rendezvous point out there using ASM, and everybody is able to just rely upon that one RP for certain groups, and that's what our solution will be. At first that would probably work because it's kind of a small, still kind of in the testing phase, and that's in fact what's being used today. But going forward, would that work? Well, there is a proposal out there that some of us have actually implemented that has to do with embedding the RP address in a multicast address. So with v6, again, there's certain bits that you can set that will flag that the RP is embedded within this multicast v6 address. So the RP address is known. So there's no need to use MSDP to find out the sources. Everybody, as long as they're using routers that understand this embedded RP, will be able to know what the RP address is based upon the multicast group, and then be able to send the packets off to the rendezvous point. Some people that think that's very attractive. It, in the spec, specifies that this is a temporary solution. It may or may not be, or maybe it won't take off at all. We need to know if everybody's okay with depending upon some other RP out there for our sources and groups to get our sources and receivers to get together. We need to hear from you guys. You still would need MSDP for an Anycast RP solution, or an MSDP-like solution at least. It's pretty simple to implement for PIM sparse mode. Intermediate, your routers again need to be upgraded to be able to handle understanding these embedded RPs, and perhaps there could be some scalability concerns because you have this big virtual flat domain instead of a bunch of little domain islands. So this is where we're at. All three of these are being used right now in the M6 bone and 6net. All three of these, meaning we have embedded RP solution, we have static RPs that are being used, as well as BSR. Those are the three ways right now that we know of a rendezvous point within the v6 world. If anybody's interested in actively participating in v6, let us know. Feel free to send me an email if you wish, and I can steer you in the right direction. Again, it's McBride@cisco.com. And that is it. Any questions before we close? Not bad. I had like 3 minutes to spare. Thank you. That's it.